So in the last video, we constructed this table up here. It took a long time to create this. But what we can see is that this table here fits the description of what we would call a binomial distribution. So here are some of the properties that allow us to state that something is binomial. These are the identifying properties. First off, in every binomial distribution, the number of trials, the number of times I'm going to do something, whether it's flipping a coin or rolling a die or whatever it happens to be, that number of trials is fixed. It's often represented by this letter little n. Each trial also is only going to be able to have two possible outcomes, which we will deem as a success, that is something that we're looking for actually happening and interested in counting, and then something that's a failure, something that we're not interested in happening. The trials are going to be independent, so every time I do something, it's independent of a previous result. For the moment, you can ignore this 5% condition, although this will show up a little bit later in the course. We'll revisit it at that point. And the final and fourth property is that the chances of hitting a success, that is of getting the thing that you wanted, is going to be the same from trial to trial. And that's often represented by the letter p. So here I state that the random variable x in a binomial distribution denotes or stands for the number of successes that we will end up with in n independent trials. Now, a lot of that can sound confusing, but let's take a look at how our dice rolling scenario meets all of these descriptions. So first off, description 1, the number of trials is fixed. Well, in our scenario in the last video, we said that we were going to roll a die 3 times. So we rolled a die 3 times. That was fixed. We weren't going to roll it until we got a 1. That wasn't the case, right? Because that would have been who knows how many possible rolls we would have needed. We said we're going to roll 3 times and then the experiment is over. And so here we've established that n is a 3. So number 1 I can say is checked off. Now I can go to number 2, which says each trial had only 2 possible outcomes, something that I would deem a success and something I would deem a failure. So here I can definitely say, yeah, a success would have been rolling a 1, whereas a failure would have been not rolling a 1, right? So rolling a 2 or a 3 or a 4 would have been considered a failure. So I've definitely satisfied here property number 2. Number 3 we already talked about. The trials were independent. So I'll say here that dice rolls are independent. So that one's super easy to check off as well. And then I'll take a look here over on the side. Number 4 is my probability of success. Is the probability of rolling a 1 always the same every time I re-roll the die? And yeah, it's not like we switched dies or went to a trick die halfway through or a die with a different number of sides. We re-rolled the exact same die every time, and that chance of rolling a 1 was always 25%. So I'll go ahead and say here that the chances of rolling a 1 was always 25%. It was fixed. And so note that gives me that p is equal to 0.25. That's the symbol I would use to represent that. So definitely I have here a binomial distribution. Now, one of the things, again, that's cool about these different distribution types is that if I have a scenario that fits this distribution type, there ends up being some awesome patterns and shortcuts we can capitalize on. Now, here's a big, scary binomial formula that allows us to compute all the different things that we were kind of seeing up above in the previous example. If I wanted to find the probability that the number of times I rolled a 1 was equal to a specific number, I would just have to multiply these 3 things together. Now this is kind of strange, but you can maybe at least briefly see what this formula is for. It's mostly just here to be scary and to help us value what our calculator can do, but we'll talk about it super briefly. This p in here represents, again, the chances of rolling a 1, and it's going to be, we're going to need to roll a 1 a certain number of times when we calculate probabilities in our table. Like up here, in certain scenarios we had a different number of y's each time, which corresponded to a different number of 25% in the multiplications. We're also going to have a 1 minus p, chances that I don't roll a 1, and those are going to have to occur a certain number of times. And then we saw that in a couple of the examples up above, we had different orders or different numbers of possible arrangements that we had. And so there were jumbles, ways that I could think of reorganizing these different letters. And that is accounted for by this crazy thing up front with all the exclamation marks. Now again, this formula here is never going to be something that we are going to use directly. It is really just here to look scary. So we're going to focus instead on how do I get my calculator to use this formula for me. So what are the calculator commands that I'm going to need to use to access these different resulting values in my table? Well, to see that, we're going to go ahead and try to recreate our probability distribution using this fact of the binomial distribution and our cool calculator commands that we have here. So I'm going to go ahead down below and I'm going to actually create a new table involving the same calculations or the same values ultimately that I had before. So let's see how we would actually go ahead and do this. Over here I'm going to have x and p of x, so it's going to be set up exactly the same. I'm still going to be talking about the number of times that I could roll a 1 in 3 tries. So I either get 0, 1, 2, or 3 of them. But I'll show you really quickly here how this first calculator command actually works, what is called the binom PDF. Now, this calculates the probability for a single x value. That is, it can get me a probability that's going to be across from any number in my table. And so I'm going to go ahead and actually use this calculator command 4 different times to find each of the probabilities that is going to be located here. Okay, so let's see how this would work. If I want to find the probability associated with x being equal to a 0, I need to go ahead and write in a binom PDF, and then these 3 values associated with my given scenario. So first I have to include n, which is, again, we saw up above, the value of 3. I'm going to include p, the chances of getting a success, which we saw as 0.25, and then I'll include x, which is the number that I'm trying to find the probability for. Now once I do this, I can actually go to my calculator and type all of this in, and then have the calculator compute the resulting value. The value that I'm hoping that the calculator produces will be exactly this value, 0.421875. All right, so let's go to the calculator and see if it can actually produce this. So to find this on the calculator, I'm going to be going ahead and clicking on my second button, and then clicking this vars button. You'll see up above it in blue or in yellow on your calculator, it says distur, or it's short for distributions. So when I click on that, a whole bunch of different options should pop up like this. Now I'm actually going to click the up arrow to kind of scroll through my different options. And you'll see that down here I have a binom PDF. If I click that, one of 2 things is going to happen. I'm either going to have this fancy menu, which is going to ask me for n, p, and x, which again is going to look like 3, 0.25, and 0, and I can paste it. Or I would just start by having this on my screen already, and I would have to fill in the numbers using the comma button. Keep in mind, the comma button is right here above the 7 for when you need to use it to offset these values. Once I click this, it should calculate, and look, there's my value, 0.421875. So I'm going to go ahead and record that down, 0.421875, exactly the same as what we calculated the long way up above. Notice that actually all of the rest of these binom PDFs are going to be set up pretty much identically, because I still am rolling the die 3 times. There's still a 25% chance to get a 1. I'm just going to change how many times I want to get that. So it's really just this number at the back that's going to change. So if I go to my calculator, I can go back through the menu options. I can click second vars, go find that binom PDF, click it, and change my value. Once I do that, notice it's changed here to a value of 1, and when I click enter, there's my next value, 421875. All right, so I can say 0.421875. Now sometimes to be a little bit faster here, what you can also do is click on the second button and then enter. that will actually pull up the last line that you typed in the calculator, and if you use your arrow keys, you can go back over different numbers and edit them, which is really helpful here if I want to, say, change this just to a 2 and hit enter again. It saves me from having to go through all the menu options multiple times over. So now I have this value, 140625. So I'm going to go ahead and write this down. This would be binom PDF 3.25, 1, and I get 140625. For the last one, I get pretty much the exact same setup. Oops, sorry, this should have been a 2 up there. I'm going to go ahead now and have a value of 3. And if I test this out on the calculator, I'm going to go ahead and do that by clicking second and enter, going over and clicking on, or changing my value to a 3. And when I hit enter, I get 0.015625. So that's 0.015625. Again, what you'll notice is that I was able to get those values extremely quickly, and they are the exact same values that we had previously established. So these calculator commands can really help me access all of the numbers that exist in my table very, very quickly. What we'll see in the next video is how I can start to use this to calculate some probabilities more efficiently, and also we'll see how to use this other calculator command of a binom CDF.